Yeah, students, are you able to see the PPT?
Yes, sir.
Okay. Okay, so yesterday we discussed about the model of this JFET and we come to this conclusion. This is the model of JFET. Now we will do just like BJT transistor, this MOSFET, this JFET can also be connected as common source or common drain or common gate, right? So we will see the analysis of this JFET for these three configurations. We'll see first analysis of JFET, right? And here we will first see common source amplifier. Right? CS. In short, it is called as CS, common source. So the circuit diagram for this common source amplifier will be like this. This is our JFET, right? This is gate, drain, and source, right? And now here we have connected the signal which we want to amplify. V in. And here we will connect one capacitor, right? This is our capacitor C1. Now at the source terminal we will connect one resistance. This is RS. At the drain we will connect another resistor. This is RD. And here we will connect the battery VDD, right? So this battery VDD is used for the biasing, right? VDD battery. Now here gate and source. Already we discussed yesterday that this gate and source will offer a very high resistance, right? So this resistance is denoted by this RG. Okay. And there is one capacitor you have to connect in parallel to RS, and this is our capacitor C2. And here we have another capacitor C3. This is our load resistor RL, right? So here we will take the output. Across this RL, we will take the output V out, right? So this is the, and source we have connected to ground. So this is the figure of common source amplifier, practical figure of common source amplifier. So this is my figure number 1, right? Common source JFET amplifier. Okay, so in this VDD is biasing voltage. V in is the signal. Signal which is to be amplified. Right? So this V in we have applied between gate and source. So this is applied between gate and source, right? And the amplified output is taken across drain and source, right? So you can see here across this drain and source we are taking the amplified output. Now here C1 and C3 are the coupling capacitors. C1 and C3 are coupling capacitors. Right. So see, the meaning of coupling capacitor here is, see, this is C1. V in is a AC voltage source. So this C1 will allow the AC voltage source to pass through it, right? Whereas you see here this DC voltage source VDD. So it will be blocked by this C1. C1 will not allow to pass this side, right? And you see at the output side, C3 is a coupling capacitor, so the amplified signal, which is a AC signal, will pass through C3. Whereas this VDD, this is a DC voltage. For that, it acts as a open circuit, so it will not allow that VDD to pass through it. So at the output, you will get only the amplified AC signal, right? So it will not allow the DC voltages to pass through it, right? And C2 is a bypass capacitor, right? So if now we are talking about the this input signal, which is a AC signal. For AC signal, this will act as a short circuit, right? So if it will be act as a short circuit, then all the current will pass through it. No current will pass through RS. And if no current will pass through RS, then there will be no voltage drop across RS. And if there is no voltage drop across RS, then all the amplified output you will get at the output V out, right? So if you will not connect C2, then what will happen? The current will flow through RS and there will be voltage drop across RS, and the voltage gain will reduce, right? For that we have used this C2, and C2 is a bypass capacitor. C2 is bypass capacitor. Okay, and if C2 is not used, then there is drop in voltage gain. There is drop in voltage gain. And why there is drop in voltage gain? Because this C2 for the AC signal, it is a short circuit, right? So it will allow all the current to pass through the short circuit. So across the short circuit, there is no voltage drop. So there is no voltage drop in the source and ground path. That's why all the voltage you will get at the output. Okay. So now this is the diagram of uh, common source amplifier, right? Now we will draw the AC equivalent, because we are doing the analysis, and AC analysis we are doing right now, right? So now what we will do? Okay, next page I will do. Now AC equivalent. Circuit. of figure 1. So for drawing the AC equivalent circuit, what we have to do? Yes, somebody can respond. For drawing the AC equivalent circuit of this figure 1, what we have to do? What we have to do with the capacitors? First thing, what we have to do with the, yeah,
Making capacitors open circuit.
Short circuits.
short circuit.
Short circuit.
Yeah, because see AC means there is some frequency is there, right? XC. What is the formula of XC? Capacitive reactance 1 by 2 pi FC. For F is equal to 0 means DC. For F is equal to 0, XC will be infinite, right? This means for DC it is a open circuit, and for some high frequency, this is having a low resistance, right? So for whenever you are making a AC equivalent circuit, then whatever capacitors you are seeing, make those capacitors short circuit. Whatever DC voltage sources you are seeing, replace the DC voltage source by a short circuit. Means, see here you are seeing one DC voltage source. This will DC voltage source means like this. VDD. This is your VDD, and it is connected to RD in this way, right? This is the circuit diagram. So make it short. So making it short means connecting it to the ground, because if you make it short, then this you connect this to ground. Okay, right. So this we have to do. So what we have to do? Short circuit. Circuit all capacitors. Right, and replace DC voltage source by ground. Right. So if you do that, then we will get some this type of circuit. See here this C1, this is short circuit, right? This is RD and this is connected to ground because there is one voltage source VDD, and so this is a drain, gate, source. This is RS. Across this we are having one capacitor. That capacitor is short circuit. What is the name of this capacitor? C2. Right? And here we are having one coupling capacitor C1, C3. This is short circuit, and here we are having load. RL, and we are taking output across this RL. This is V out. This source is ground, right? In this way, you will get this circuit. Yeah, RG is also there. There is RG. This is figure 2, right? Now I will rearrange this figure. I will rearrange this figure in this way. This is the voltage source and this is V in. Now you see this RS and this capacitor C2, which is short. So if there is a short circuit across any capacitor, then you can remove that capacitor. So directly we will connect this. We will make it short here. Okay. Now you see this RD register. It is connected to ground, right? So I will connect it to the ground in this way. This is RD, right? Because this source is ground. So directly I have connected this to ground. So here it is drain, gate, source, and across this we are having RL, right? And across this RL we are taking the output. This is our figure 3, and this is our AC equivalent circuit. AC equivalent. AC equivalent circuit. Circuit of figure 1, right? So whatever was our figure 1 and its equivalent AC circuit is this, right? So in this way we have drawn the AC equivalent circuit. Now here this RG, right? So what is this RG? This is the resistance between gate and source, right? So this is not an extra resistance which you have connected. This is the internal resistance which is offered between gate and source, right? And it will be very high, right? So if it will be very high, then you can find all the V in is available here. All the V in is available between gate and source, right? Because RG is very high. So all the V in is available at the gate and source. Okay, right. So now what we will do? We will draw the JFET model of this circuit. Now here one thing I want to remind you. We are for taking the output we have connected RL. But sometimes if you will not connect RL, then also you see RD, drain resistance. Across this also you can take the output. Okay, across RD also you can take the output. So, but here we have connected one RL, right? So now if we see the model which we have drawn here, right? This model, JFET model. So here in this JFET model, this is the model of this transistor, right? This is a JFET. Here it is gate, drain, and source. Its model is shown here, right? Its model is shown here. But externally we have connected to this model one V in. We have connected here one V in, right? And we have connected some resistor R D and some load resistance, other things we have connected. Okay. Now this in this model voltage between gate and source. Since the resistance between gate and source is very high, that's why whatever V in you will apply, that V in is available here. That V in is available here. So you can say that V in is equal to voltage between gate and source. Okay, it is a voltage between gate and source. Okay, so this type model we have to draw for that circuit, whatever AC equivalent circuit we have drawn. So now common source, JFET model of figure number 3. This figure, right? AC equivalent circuit, this figure we have drawn, its model we will draw. So we have the model this type. Here we have RL, Across this we are taking output. Here we have RD. We have RD, right? Now you just come to this model. So this is the transistor model. VDRDS, this is on drain to source resistance. So now this resistance we have to connect RDS. Then there is current source, right? Its value is GM V GS. See here, this GM VGS. Okay. And here this is source. This is your source. Here this is drain, right? This is your gate, right? And here we have connected V in. Here we have connected V in. Okay. So this is here, this is drain. So here you can see there is one resistance basically, and this resistance is resistance between gate and source, right? But its value is very high. The value of this RG is very high. So here we can write this: since value of RG is very high, so we can drop it. We can drop it because its value is very high, so it can be considered as an open circuit. So we can drop it. That's why here you can remove this RG here, right? So this is the model, and here you have this IL, right? And this is the drain current, ID. This is a drain current, right? So this is your figure number 4. Right? So this is your JFET model. Model of figure number 3. Right? This is figure number 4. Right? So whatever figure number 3 you got, its JFET model is that. Right? Okay. So now here you can see there are three resistances, RDS, RD and RL. They are in parallel. Okay. So I will remove these three resistance with a resistance. Let RD is equal to RDS parallel to RD parallel to RL. Right? Now here this RDS, it is the on resistance, internal or on resistance of a MOSFET, right? And its value is very high as compared to RD and RL. In practical, I'm talking about the practical. See, when we are drawing these models, so these models we are drawing by assuming certain assumptions also, right? So here this when we use JFET in some application, then the RD and RL, whatever RD and RL we select, its value is very much less than RDS. So now you see, if I write here, suppose 3 ohm parallel with 50 ohm, right? 3 ohm parallel with 50 ohm. Then what result you will get? What will be the result? What is the parallel combination value you will get? It is near to 3 ohm or it is near to 50 ohm. Yeah, students, if two resistances you have connected in parallel, then the parallel combination value will be near to the lower resistance or near to the higher resistance.
Lower resistance.
Yeah, because you
Lower
see
resistance.
3 into 50 divide by 3 plus 50, 53 ohm. So it is approximately, right? It is approximately near to 3 ohm, right? It is basically somewhat lower than the lower resistor. Okay. So now with the same concept, since the value of RDS is very, very high as compared to RD and RL, right? So this can be approximately written as RD in parallel with RL, right? Why we have written this? Since RDS is very high, as compared to RD and RL. Okay. So now we will replace this RDS, RD and RL, this parallel combination, by a resistor RD, whose value is approximately equal to RD parallel to RL, right? Whose value is approximately equal to RD parallel to RL. Okay, so so today evening, do you have that class, industry driven course or not? No, na? Okay, then your last class end at what time?
4.
At 4. Okay. Okay, then at 4:10 I will take the class. Okay.